Welcome. Thank you for joining, everybody. Are you ready to learn? This is math from the void. Math coming at you from pretty much out of nowhere. You don't see anything that's going on my end. Like if my eye were twitching really strangely, you wouldn't even notice it. You're here to learn. We're continuing our AP Calculus Free Response series with a problem from 1995. Some of these older problems really emphasize pre-calculus skills, and some of the problems we're going to be looking at are going to involve pre-calculus topics like the domain and the range. Now, the domain is going to come from three major domain restrictions you should know about. If you're not familiar with them, go check out my video on domain restrictions. The three main domain restrictions are the rational function, the even radical, and the logarithm. Now, we don't have any logarithms in this equation, but we do have a rational expression, right? We have a big fraction with some x stuff going on in the bottom. And we also have this even radical in the denominator, so we have to be careful about a couple of things here. First, let's work with the fraction. So we need the denominator to not be 0. So this thing in the denominator, which includes the square root, needs to not equal 0. And that means that the inside of this radical needs to not equal 0. So let's find what values would make this equal to 0. We're going to use the quadratic formula, but we're going to kind of use the non-quadratic formula. I know that sounds silly, but let me show you what I mean. Since we're interested in this not equaling 0, we're going to make sure that x is not equal to negative b plus or minus the square root b squared minus 4ac all over 2a. So it's almost like we're using the quadratic equation, but we're saying that x is not equal to that. And if we use this quadratic formula, we see that there's a negative inside of the square root. So, in fact, x doesn't have any restrictions that could make the denominator equal to 0. Here we would have square root of 3i over 2. And since that's not a real number, we don't have any real numbers to worry about that could possibly make the denominator equal to 0. So there are no domain restrictions based on that. Let's also take a look at x squared plus x plus 1. That's the even radical. So the rule for even radicals is that they must be greater than or equal to 0. Of course, it cannot be equal to 0, otherwise we would have a 0 in the denominator, and we just proved that that can't happen. So if there are no real zeros, what does that tell you about this? There are no real zeros. So it tells you that this is always going to be greater than or equal to 0. Specifically, it's going to always be greater than. And if you don't believe me, you can take a little look at the sketch of x squared plus x plus 1. It has an axis of symmetry at negative 1/2. And if you plug in negative 1/2, see what you get. You get positive 1/2, which means the vertex of this parabola, and therefore the minimum of this expression, which is a quadratic expression, is 1/2. And it's always positive. So we don't have any restrictions. The domain is all real numbers. Or if you'd like to put it from negative infinity to infinity, that's fine as well. Now, They gave us a viewing window in the original problem, but I've cropped that out. It says, in the original viewing window provided below, sketch the graph of f. Sketching the graph is going to come down to us being able to identify any vertical asymptotes, horizontal asymptotes, those kinds of things. In fact, question C asks us for the equation of each horizontal asymptote. So it's going to be useful for us to use things like the derivative, understand regions of increasing and decreasing, also understand regions of concavity. I have a feeling that back in this time, it's possible that this structure of equation was something which students would have been familiar with and would have been encouraged to memorize. So what happens here is we get a bit of a bump. That's more or less what the graph's going to be looking like. We want to show that this is an accurate sketch, though, by finding some special points. So let's look for the y-intercept, for example. If we want to plug in 0, f of 0, we'll notice that that's just going to be 0 because the top is going to be 0, and then the bottom is going to be something like square root of 0 plus 1, overall 0 divided by any number that's not 0. It's just equal to 0. So there we are. Then let's analyze the sign by using a chart. We can analyze the sign of this function by looking at 2x, and then we have the square root term, which we know is always positive. We looked at that in the domain. It's always positive. And of course, 2x is 0 whenever x is 0. It's negative anywhere before, and it's positive anywhere after. Therefore, the overall result, the overall function, is going to be negatively valued whenever x is negative, positively valued whenever x is positive. That's some good progress so far. Another thing we should look at is the derivative. So let's take the derivative. And we're going to do that by using the quotient rule. Remember, low d high minus high d low. So here's low d high, it's just 2, minus high d low. Let's be careful with that, because this is the same thing as x squared plus x plus 1 to the 1/2 power. So its derivative is going to be 1/2 x squared plus x plus 1 to the negative 1/2 power. And then because of the chain rule, we multiply by 2x plus 1. This is all over the square root squared, which just stays x squared plus x plus 1. Now this looks really complicated, but what we can do is this nice little trick, because here we have an expression to the 1/2 power. Here we have an expression to the negative 1/2 power. What we can do is multiply the top and bottom expressions by the 1/2 power. We can multiply x squared plus x plus 1 to the 1/2 power on the top and on the bottom, which we already sort of have on the bottom. So what this is going to do is it's going to distribute and cancel this. It's going to distribute and remove the root. So here we have x squared plus x plus 1 with no more root times 2 minus 2x times 1/2. I guess I can cancel those things, can't I? And this is completely canceled here because we're multiplying by this 1/2 power. And so that's simply going to be x times 2x plus 1 all over x squared plus x plus 1 to the 3 halves now. So let's simplify the top a little bit. That's going to give us 2x squared plus 2x plus 2. Oops, sorry about that. I backed up a little too much. 2x squared plus 2x plus 2 minus 2x squared minus x. And this is now all over x squared plus x plus 1 to the 3 halves. Some last simplification here. It's going to leave us with x plus 2 over x squared plus x plus 1 to the 3 halves. Now if we analyze the derivative on a sign chart, we have two main factors. We have x plus 2, and then we have this expression, which again we know is always positive, x squared plus x plus 1 to the 3 halves. That is always positive. It's never 0, it's never negative. The top factor just has a 0 when x is equal to negative 2. Anything to the left is negative, anything to the right is positive, which means we have a critical point, and more specifically, we have a minimum at x equals negative 2. So that tells us a little bit about what's happening on the graph as well. Always negative, but we do have a minimum at negative 2. Let's find the y value there. We can call this a relative min. Let's find the y value there by plugging in 2. So that's going to be 2 times 2. Sorry, by plugging in negative 2, excuse me. That's going to give us 2 times negative 2, thank you, over the square root of negative 2 squared plus negative 2 plus 1. Now this is the original function that I'm plugging it into because I want to find the y value of this point. I'm going to get 4 minus 2 is 2 plus 1 is 3. We could also call this negative 4 root 3 over 3. That would be acceptable. If you want a value for that, I gotta guess it's somewhere around negative 2.3-ish. I don't know exactly, so we would want to be safe and just label it as negative 4 root 3 over 3. And that's going to be our minimum point. But then I want you to notice something. The derivative is negative leading up to it, but positive afterwards. So positive afterwards is going to indicate some kind of shape like this. But how high up is it going? Well, that's where parts B and C really come together. There are horizontal asymptotes in this graph. So we can do parts B and C kind of simultaneously. We only have a little bit of info. We know that this is both a x and y intercept. We know that this is a relative minimum value, so the graph is going to do something like this. But if the function needs to stay negatively valued, according to this part of the chart, it needs to stay negatively valued when x is negative. That means that there's some kind of boundary. Maybe it's at the x-axis, or maybe it's somewhere else. We can be confident that it connects here. We would technically have to look at the second derivative in order to even further analyze the concavity, but this is a decent sketch for now. Let's talk about the horizontal asymptotes, and it'll give us some information about the graph. So the horizontal asymptote is equivalent to looking at the limits as x goes to positive or negative infinity. So first let's look at the limit as x goes to infinity of 2x over x squared plus x plus 1. And of course, if we try to plug this in, it goes to infinity over infinity, which is undefined, so we're going to have to work with this a little bit. what are we going to do? Well, what we're going to do is we're going to divide the top and bottom by x. So we're going to multiply this by 1 over x. And then on the bottom, we're going to do that as well. But what that does is that actually divides the inside of the root by x squared. That's the same as dividing by x if we were not in a root. X over x squared. And here we have 1 over x squared. Now the convenient thing about this on top is that it completely cancels. Here it completely cancels to 1. And here, if we send x to infinity, the bottom is getting bigger faster than the top of these fractions. So they're just going to 0. So this is just going to 2 over the square root of 1, which is 2. And now we have a horizontal asymptote as x goes to infinity. So we know that x is not going to get any higher than 2. In fact, it's not even going to reach 2. Like that. And I can label this as 2. Now what about on the left side? The left side actually isn't too bad, because if I were to plug in negative values, notice that the squared feature on bottom would stay positive. So this really is the same as the limit as x goes to infinity of negative 2x over the square root business. But then we can just take the negative out in front of the limit, and this would be the same as negative limit as x goes to infinity of 2x over square root of x squared plus x minus 1, plus 1. But we know that this limit is equal to this one here. We know that this is equal to 2. So this is simply going to be negative 2. And there is our other horizontal asymptote. Now, where is negative 2 compared to negative 4? Rad 3 over 3. Well, just to be clear, let's show that this is actually less than negative 2. And that's because negative 4 rad 3, if we multiply both sides by 3, how does this compare to negative 6? Well, if we square both sides, this would be 16 times 3, which is 48, and this would be 36. So we know that this number is larger than 6, which means that this is more negative than negative 2. So here's the boundary for negative 2. And as I mentioned earlier with some rough calculations, is that negative 4 rad 3 over 3 was approximately negative 2.3-ish. So because of that, that means that this minimum value is reached, but that the rest of the graph kind of curves upwards. There's both a sketch and my 2 horizontal asymptotes. So the last question goes along with the sketch as well as our chart. It says use f prime to justify your answer for the range of f. Well, we know that the asymptotes are 2 and negative 2, so someone could think that the range is simply from negative 2 to 2. But you might remember that horizontal asymptotes can be crossed as long as we're not crossing them all the way to the left and all the way to the right. So the fact that this is crossed at this value is not a big deal. And we don't even need to figure out where it crosses that value. We just know that it does because our minimum value is lower than it. We also know that our minimum value, which is a relative minimum, has a negative derivative to the left of it, which means it's increasing if you go to the left. But it never surpasses the negative 2 line. And on the right, similarly, it never passes the positive 2 line. So the absolute minimum here is negative 4 rad 3 over 3. That's going to be a hard bracket on the range there, comma 2 with a parentheses because that asymptote is never reached. this is your range. So, very interesting question from 1995. That's the A, B, and this is a great place to stop. I'll see you next time in the void.